all set to go. I can start introducing our next presenter. We have Allan Struthers with us from Michigan Technological University. We're very happy to have him here, and he will be presenting on experiments, data, and models for nonlinear electrical circuits. So I pass it on to you.
Thank you, and thanks again to all the organizers. And this is going to be a little bit different. This is partly class experience and partly trying to encourage people to get brave about electric circuits. So we're going to give you a little background of Michigan Tech. We're an engineering school, and about 80% of our student body has a science or engineering major. And essentially all those students complete a linear algebra and ODE sequence. And a lot of them are electrical engineers, and a lot of them are mechanical engineers. But they don't have to take all that many courses to get a math minor, and it fits pretty well into most technical degrees. That's sort of by design. And lots of students choose to complete a math minor. And there's a senior level course, Nonlinear Dynamics and Chaos, that's a very common elective for these students. And a project is a common feature, common component of this course when I teach it and when other people teach it. And the students like to do chaotic circuits. So what we're going to describe is a sequence of fairly simple electronic circuits. The target is to get to a chaotic circuit. I'm sorry, I need to move this Zoom window that has set itself right in front of the, no, I don't, I'm just going to talk. Okay, so we're going to describe a sequence of circuits, and the target is to get to a chaotic circuit. Now, a chaotic circuit has to have at least 3 variables in it, and it has to have a nonlinearity, and that's driving the chips, the circuit design that we're using. I found out that the students struggle with this circuit design. I'm going to put some references up just at the beginning, just because otherwise I'll forget. We've got a simple chaotic circuit reference. We've got a reference that's going to turn up that is where my students were taking designs for circuits from. We've got a couple of standard differential equations books, and we have a couple of dollars worth of an analog multiplier. That is a physical chip. And we've got an eBay oscilloscope, and I'm just doing that so that I don't forget. So the students have really often chosen to build chaotic circuits, and since they were very much into that, I decided that I would focus the class on a particular system of ODEs. This is called the Rosler system right here. And A and B and C are constants. They're traditional values. They are what you would tune to go from a very deterministic system to a chaotic system. It's named after a guy called Rosler. And they have always struggled to build functioning circuits. And this includes students, electrical engineering students with a lot of circuit experience. They've struggled to interpret the circuit diagrams. They have particularly struggled to explain what they are doing in a final presentation to the rest of the class. And that is an important component of what I'm trying to get them to do. So I decided to try to incorporate a circuits tutorial into this class and get the students to construct the circuit that models this. Primary source for this was a proposal from reference 2 that we showed up above. All the students, this is unusual, all the students report some previous experience building circuits with soldering irons and claim to remember circuits from ODE's class. It's a senior level class, so they all say that they know how to do this, and essentially none of them, including electrical engineers, can do it. So they struggled more with building the circuits than I thought they would, and I started building some tutorial materials. And we're going to talk a little bit about those tutorial materials, see some student work, and try to think how we could explain things. And everything here is completely safe, is the first comment, okay? I've got a comment from Matt Olkowski saying it's a little scary. And we're trying to make it less scary. I'm just going to show you what this Rosler system looks like, solved in Mathematica and plotted. It's got an X, Y, and a Z, and that is what a phase plane plot looks like. It has a chaotic attractor. It goes around this loop, sort of in X, Y, and occasionally jumps over the loop in Z. That is what it looks like as a function of X, Y, and Z. Oh, brave. And you can sit and see that it goes round and round and round. It slowly spins out, and then it jumps up and goes over the top of the ski hump. It does it again. The reason it's chaotic is that you don't really know how many of these trips around the attractor it makes before it goes over. This is a simple standard example. In fact, it's the simplest example. It's simpler than the Lorentz system. And here is a picture of a student-made chaotic circuit. We're going to do some tutorial stuff, so I'm going to explain what the white thing is. The white thing is called breadboard. The wires are pretty obvious. These round things are variable resistors. The little sausage things are fixed resistors. This little square thing sitting in the intermediate thing is called an op-amp. That is actually an LM411, I think, but I can't read the number on it. And these square things are capacitors. And all the wires are connecting it. And the power runs down the side of this, and it's powered by a 9-volt battery. For prop, we have a 9-volt battery. Actually, this one is powered by two 9-volt batteries, which is a little problematic. Students putting this together struggle a little bit, and it could be much more organized than it is. But this is not the worst one that we've ever seen, and this one does indeed work. Okay. There is a block diagram that's taken from reference 2, and it features in here, I'm going to make this bigger. There we go. Features in here a little thing that says AD633, and that is a analog multiplier that used to cost $2 during the middle of COVID, cost $20, and now costs $2 again, which is some progress. And that inexpensive analog multiplier gives you the multiplicative term. And fortunately, it's incredibly clear what it does. The loops, and you can see loops in this diagram, and why it is a Rosler ODE is far from clear to most ODE students, and that includes EE and physics majors who make up a significant fraction of this class every year. You can ask questions. There's resistors. This is a variable resistor down here. And you can sit and see that would be intimidating to, presumably intimidating to Matt. But the AD633 data sheet, it's got some technical specifications, but I just snipped a little picture from it. It's got 8 legs, plugs into that white breadboard, and 2 of them are power supplies, 9-volt batteries. And then it tells you what it does. The output voltage W is a voltage Z plus a voltage difference times a voltage difference divided by 10 volts. And you go, why is it divided by 10 volts? Well, because the design voltages in here are plus or minus 9 volts. And that means that if you divide by 10, you're going to keep it in range and it's not going to do anything exciting. And 9 volts is completely safe. The safety officer at our institution was quite unconcerned with 9-volt objects. So what's the target? Well, the target is a convincing, accessible introduction to nice, simple circuits. And we're starting from clear statements of Kirchhoff's laws and specifications of the things that you see in your ODE book description, capacitors, resistors, and inductors. And we're going to have to add a multiplicative voltage source to that. We want to make a Rosler-like system. And I'm fully aware that dinner is coming. And I discovered that you have to go further back to make the students comfortable and happy. And so you get exciting things. Electrical components are connected by wires which are joined at nodes. In other words, the black lines are wires, and the places where the black lines join are nodes, and the squiggly lines, the squiggly objects, are either resistors, capacitors, or inductors. Capacitors store charge. Students know what charge is. Kirchhoff's laws, and we're going to talk about them in a second, give the ODEs for the time-varying charge stored on each capacitor in a network. The students find capacitors good as a fundamental thing. And voltage differences drive changes in the charge. So this is all just to try to make it clear what's going on. We're going to see what the students wrote down when asked to design a circuit and turn it into ODEs in a second. But first of all, we need to talk about what the voltage drop across a capacitor is. That is essentially the definition of a capacitor. Delta V equals Q over C. Q is the charge. Ohm's law, voltage drop across a resistor, delta V equals I times R. It helps students to know that capacitances are tiny, but resistances are big. And then there's this other thing called an inductor, and it also helps them to know that inductances measured in the standard units are small. Their unit there is called a Henry. There are variable capacitors that you can buy. These are very, very cheap components. You can buy a box of them. I'm going to wave a box in front of the camera. That's a box of, I don't know, 100 capacitors that cost $5. There are different sizes and there's variable ones as well. So variable capacitors can change their charge by turning a dial. Variable resistors change the resistance by turning a screw. And also there are variable inductors, and they all work pretty much the way that they get described. We got Kirchhoff's laws, pretty short. Sum of the currents into a node is zero. The sum of the voltage differences around any closed loop, every closed loop, is zero. And you need to talk about these, and then you need to demo how to set them up. We're going to set up things on breadboard, and breadboard is just this white stuff. All these holes are connected together underneath, and all these vertical holes are connected together underneath. And the thing in the middle is specially designed to have these little op amps be able to sit in it. And that is indeed an AD633. If we're a little brighter, you'd be able to see that. They come in different sizes, as you will see. Oh, and they're cheap. So this is an oscilloscope. And you go, how much is an oscilloscope? Well, it's a digital oscilloscope. They used to be expensive, but now they cost $170 on eBay. That's the price yesterday. May have changed. It takes a little while for some of them to come, but this one came pretty fast. And it has a useful thing. This green thing down here is a signal generator. And time permitting, we're going to point it actually at a camera, actually at the oscilloscope sitting over here, but I took pictures just so that I could say what we're doing. And what we're actually looking at is the input and output from this simple circuit down here, which has got a capacitor and a resistor. It's plugged into the signal generator, which is generating the yellow square wave, and it is producing as output this blue curve that is the voltage across the resistor. Completely safe. It says it's got 331 millivolts. In other words, you can put it on your tongue, it doesn't sting. Any questions? What we're going to do? We're going to maybe sit and play with the oscilloscope a little bit. Going to see what else we can do. Oh yeah, I've got to zoom in on my circuit. This is a resistor. The stripes tell you what its resistance is and whether it's an expensive resistor. And this is a capacitor. And I don't know if you can see these little numbers on the side of it. That actually tells you what the capacitance is. These two, the leg of the capacitor and the leg of the resistor, are connected together, as is the green probe. So these are all at the same voltage. The circuit goes in from here through there, up to there, back to there, and back. And that's going back to the signal generator. The language stripy sausage thing comes from a student, and I kind of liked it. A standard oscilloscope has a button. It's this button here that says XY mode curve that will draw you a phase space. In other words, this is now the 1 and this is the 2. It's changed the color to nice purple to make sure you know you're doing that, because it can get confusing. If I went down to that XY mode curve, I'd be able to go back to my 2 things. This is dynamic. It's in a run mode, and it's taking a shot every time it goes through, and it does that completely automatically. You really don't have to worry about plugging it in and not seeing what you think you should see. Again, we're still in the same circuit down there. It's not an exciting circuit. This is the exciting circuit. It's an RC circuit. Well, okay, I've got a resistance of 1 ohm and a capacitor of 0.1 of a farad, which is a chunky but not impossible capacitor. It is a tiny little resistor. And I'm just drawing a picture of this. There is V1 and V2. You go which one's which. I go the blue one is V1. And there's V1 versus V2. And you see it's not connecting back up at the top because this is doing a actual physical jump. Well, physical jump's a little funny, but inside the ODE it's doing a jump. I'm going to do a triangle wave instead. All I changed was change that to triangle wave. Oh, and I added an inductance. The inductance gives you a Q double prime term, which clearly changes the nature of the differential equation. And of course, I'm in Mathematica, so I can run these things. And if somebody wants me to change this back to a square wave, I would be delighted to do so. That is the picture. This is the initial condition. I started off at 0, 0. As people have been saying, it doesn't really matter. And it zooms into this shape. And you can go and look at those shapes on the oscilloscope, and you can work out, estimate the parameters that are actually in your circuit. The resistance is not exactly what's written on it. It's within 5% or 10% or 1%, depending on the quality. So I have the students in the chaos class design circuits. This is an attempt to make sure they can write down ODEs, and Sarah made a beautiful circuit color-coded, and so I took Sarah's circuit. So you get to go look at this. This is a resistor. It's called R1. This is the standard handwritten symbol for an inductor. It's called L2. Apparently it's 200 millihenries. This is R2. It's a resistor. These are capacitors, and that is the standard sign for capacitor as drawn by Sarah. She has indicated that this is going to be loop 1 going in this direction, and this is loop 2 going in this direction. We've got a capacitor in the middle as well. They've got values against them. And this represents an AC voltage source. I know it shows a sine curve, but it could really be absolutely anything it wanted to be. And she's writing down the ODEs there. What is this? This is around the first loop. The voltage is summed to 0. She forgot to include the voltage source. I didn't notice when I graded it because it was so pretty. And this is the voltages around the second loop, adding up to 0. And this is that the currents into the node, and she chose this one, add up to 0. And the question, of course, is, does it matter which loop you chose? You could choose this one and this one, or you could choose the big outside loop. And the answer is, of course, no, it doesn't. And if you subtract these two, you'll see that you get the ODE for going around the outside loop. The students find out that if you don't put an inductor in a loop, it's not a second order equation, and that will produce a little bit of excitement. Okay, we can simulate Sarah's circuit. All our students can do this. Your students might not be able to. Depends on their background, but our students have taken a lot of Mathematica stuff and they can do this. They can't make the pretty pictures. There's the voltage source and the voltage across R1, something you could measure with your object. Yes, sorry, Matt, the phase is 2 voltages. It's the one current, 1 voltage and horizontally and the 2 voltage vertically. Further into the circuit, things look quite a bit smoother. And this is the voltage across R2, the voltage across C1, and the voltage across C2. And if you go look at this, you get an interesting thing that brings up some math. Because why does it look spiky? It looks spiky because the default interpolation order is not high enough. And you have to differentiate to get the voltage across an inductor. So I'm going to go fix that. And you should see that now looks pretty. And all of this, of course, works automatically. And the students really can do that. They don't know to change the order. There is a some phase pictures for the same circuit. They don't look pretty, but it is indeed a 2-loop circuit. It should not be surprising, and they are correct. What can you do? Well, you can do all sorts of things. You can do a frequency sweep. So I'm going to draw a frequency sweep. What that means is that I define a frequency called omega, and it starts at omega min and heads up to omega max. It's a linear frequency sweep. And then I'm going to go and simulate this guy. This is something that people do in the real world. It's an expensive oscilloscope. You can do this and you get a response. And that is a resonant response, exactly where it ought to be if you went and did the computation. The circuit, as shown, is underdamped. And you could go collect data for that. I'm going to go do this computation by hand that you would do That's what you would do, and that's the amplitude of the fixed response, neglecting the transients, and I can plot that. There's the natural plot. Oh, it needs to run, doesn't it? There we go, not a problem. There's the natural plot, there is the log plot, and there is a log-log plot, and people would draw this in a log-log plot because they'd want to see that the peak of that resonant frequency is at omega equals 10, and you go, does that fit? And I go, yep. What have we got there? I have done it with the simulation, not real data, but it would fit the real data as well. There is the resonant frequency prediction, and there is the numerical simulation, and the peaks line up. And you can do exactly the same thing for more complicated systems. Sarah's circuit has 2 resonances in simulation and data. And I think that's where I thought I would get to, and it was right. Does anybody have any questions? I'd be delighted to go and actually point a camera at an oscilloscope and play with it in real time. You can change the signal. It's there. I hit OK. I go to the next thing. It says sawtooth. And if I go, next up is another sawtooth, a step, a half wave, a full rectified wave, an exponent, logarithm. I have no idea what that is. There's a sine wave, which looks exactly like people would think. This is the time base. You can set the frequency in the input. And the hope is to try to go and make some instructional videos, helpful things for students and such. There you go. Oh, we need to change the time base to make that fit. And my colleague, Jason Gregerson, makes excellent videos. So what my students do is make chaotic circuits. I'm trying to get them to make better chaotic circuits and be able to explain what the connection between their circuits is and the ODEs. And they're not that great at doing that right at the moment, but hopefully they're getting better. Oh, you're way too close to me now. So Matt, that was for a standard circuit that would be typically presented in an engineering ODE course. And so it's an LRC circuit. So it's an inductor, a resistor, and a capacitor in series, and it's not chaotic. You have to have a nonlinear term in there for it to be chaotic. Did that make sense, Matt? Sorry, Matt asked, what does the resonant frequency you showed have to do with whether the circuit behaves chaotically? And the answer is nothing. That was to connect into the ODE course. Yeah. So Matt, the circuit design that was up at the top. Does anybody else get any questions?
I have a question. You had said earlier that the students kind of came into the course saying, oh, I can build a circuit. And then when they actually had to translate from the math to a circuit, it sounded like it was a big challenge. Do you feel like that the students find that as a benefit to them at the end of the course, that they can now see that connection better?
I believe so. It actually was, they've made a lot of circuits over the years, and they always take their circuit.
They take it home?
They take it home. So I thought there's a box full of electrical bits sitting all over the place here now at the moment, because and I thought there were a whole lot of chaotic circuits that I could choose from in there, and I would just show. And there was only one. All the rest of them have been saved as trophies. It's not that they can't design a circuit and then have you actually make circuits by plugging them into this thing, and it makes them for you. It makes a printed circuit board that you plug things in and solder. It's the translation from a circuit diagram into math, or math into a circuit diagram, is genuinely mysterious to almost all of them, I think. And they also describe different words. So there would be an integrator circuit and a differentiator circuit. And those are the words they would use in their electrical engineering class. You go, what does that mean? It means it's got a capacitor in it, it's an integrator circuit and some other stuff. But they were not seeing the connection between any circuit more complicated than an RC circuit or an LRC circuit, single loop, and the ODEs. And, you know, these are projects and they make a little presentation at a mini conference at the end of them. And I tell them I'm going to ask them those questions and they try to find out how to, and they just wind up going. So now they don't go anymore. They go and they are producing much better explanations for where things come from.
Interesting. Thank you.
So Matt asked if it was coming from Kirchhoff. Yes, the translation from the circuit design to the DEs is just the Kirchhoff laws. And you will find if you give students a 2-loop circuit that they cannot do it. So Matt, you're not missing anything about electricity. You're missing something about the education of electrical engineering students and physicists. Well, thank you everybody for your attention.
Yeah, thank you. That was nice.
You're welcome.
Thank you so much, everyone. Right now is actually the dinner break. So everyone can go ahead and log off of Zoom, go enjoy your meals or whatever you need to do for the next hour and a half, and then we'll all reconvene and continue.
Okay. Thank you for your attention. Bye.